Let's take a look at Lab 6. So for Lab 6, you all are going to be using red cabbage leaves to make indicator solution. So you're going to be boiling the solution to get this nice purple color. And you all are going to be using this as an indicator. So what's cool about red cabbage juice is that it turns colors when you put it in different pHs. So I'm going to go ahead and separate the cabbage out of here so that we can use just the liquid, because the liquid's all that we're going to need for this lab. Okay, so I've managed to get most of my cabbage leaves out of my liquid. It's this purple stuff over here. So we're going to use this as an indicator solution. And essentially what you're going to be doing is creating a bunch of pH standards. So what the solution should look like at different temperatures, and you're going to use that, or sorry, at different pHs, and then you're going to use that to identify the pH of an unknown solution. You'll have several of these that you're going to want to identify. So you're going to need to use a pH meter in order to determine the pH of your solution. So this is what a pH meter is. This is what we're going to be using. We're going to cover a little bit more how these things work in the following video. Now you'll notice I'm taking this out very gently and slowly. This instrument is pretty breakable, so do be careful with it. You'll notice there's liquid in this bottle. It's supposed to be in there. This is an electrolyte solution that keeps the probe stable and happy for us. So whenever you are storing these, they need to be stored in liquid of some type. You can put them back in here. You can put them in some water, but you should set them in some liquid. You'll also notice I've given you a beaker with some like weighted beads on them. Please use that to keep your pH meter upright whenever you put it in the liquid. You need this thing to stay upright and in liquid while you're working today. Whenever you use a pH meter, you should clean it off first. So before you put it in your new solution, you should rinse it. We can use a chem wipe, that's these guys, to clean it off, because we wanted to remove this electrolyte solution, so we're going to put the DI water in there. And then you can just simply put it in whatever solution you want to measure, and your pH meter is going to read the pH of it. Okay. When you're done with that solution, you move it to a new one. You should clean it off with DI water again. All right. In order to prepare it for the next one. If you want to store it in some DI water, you can just leave it in some DI water in between runs. All right, so let's take a look at what our solution does when we put different, when we change the pH on it. So you all are going to be collecting samples of this as the pH changes. Check it out. All right. And now let's change it back. All right. Very cool. Okay. So anyways, there's a lot of fun colors that happen in this lab. And you're going to have different bottles with different concentrations of hydroxide. This is 6 molar, this is 0.5. I'm going to give you a variety of them, and you're going to determine which ones are best in order to get the pHs that you want. Now you're going to be storing little aliquots of these samples of these different pHs. So you'll essentially turn it a certain color. So you'll essentially set it to a certain pH, and you'll see what color that is. So say this is our pH of 3 sample. And you're going to want to collect that. So I'm going to take some of my sample and I'm going to set it aside as a color comparison. So essentially now this is my pH equals 3. This is my color comparison for pH 3. So I know that if it's this color, it's pH 3. And you're going to collect a bunch of these. You'll want to think about what glassware is best for this, obviously. Beakers aren't going to be ideal. Now once you get all of your different pHs, pH 1 through 12, and you collect them, and you know all the different colors of all those different pHs, we're going to find the pH of our unknown. So this is our unknown that we're trying to measure. This is our original purple indicator solution, so we're going to use this to figure out what pH it is. So we're going to add some of this and see what color it turns. You'll see it turns green. So that indicates something about the pH of our solution. And you're going to have an array of different colors set up that tell you what this is. So you can compare this to your other solutions. We know it's definitely not pH 3. pH 3 is pink, so this is going to be more on the basic side. And you'll have all these different ones set up so that you can figure out what the pH is by looking at the color. So here are all the beautiful different colors of solutions you're going to be working with in this lab. Let's take a look at what you all are going to be doing for Lab 6, not Lab 7. We're going to be exploring pH in the lab and pH indicators, and we're going to do that specifically with red cabbage juice. So we're going to be making our own pH indicator. In order to understand what we're going to be doing in the lab, it's important that you understand what pH is because we're going to be working with that. So I'm going to go through some basic equations that you're going to need for this lab and some understanding that you're going to need as well. So if you are not familiar with this equation, you're going to need it. This is how we calculate pH. This is what pH is. pH is a function, and it represents the negative log of the H plus concentration. So this is in molarity of our solution. So let's say we have a solution like this one over here. If we took the pH of it, it would represent the molarity of all the different H plus ions in the solution. So for example, if we wanted to find the pH of a solution like this, that's 0.01 molar HCl, we could simply plug in this number because remember that HCl in solution breaks down into H plus and to Cl minus. And because it's a strong acid, it breaks 100% into those chemicals, meaning that if we have 0.01 molar HCl, we have 0.01 molar H plus. So our pH is simply the minus log of this 0.01. And that gives us a pH value of 2. So this is pretty acidic. On our scale of acidic to alkaline, 0 to 14. That's a pretty strong acid. Now you're going to see in the lab that we can measure pH with two different things. A pH indicator, like our red cabbage juice, or you might be used to like these test strips, and a pH meter. And we're going to be doing both of those for this lab. So you can use test strips that change colors to indicate the pH range, or you can use a liquid that's an indicator to indicate the pH range. And then we also have a pH meter, which is an instrument that's much more accurate on pH. It's going to tell us the exact value. So you're going to be using a liquid indicator that you're going to make. And this liquid indicator is going to change colors over different pHs, and that's going to let you identify the pHs. So there are a lot of different types of indicators, and you can see from this chart that different indicators change colors at different pHs because of the chemicals that comprise them. So one that you might be familiar with is methyl orange. You can see that it changes colors right around this range. So if you see it change from red to yellow, that means that the pH of the solution is likely in the 3 to 4 range. We use bromothymol blue. Actually, in the last lab, it was that blue solution that turned yellow when you mixed it with acid. And you can see that right around when it changes, it's going to identify our pH in this range. Another one you might be familiar with is phenolphthalein. We used phenolphthalein in Chem 121 when you were titrating solutions, and you can see that it changes color right around in this pH. And so knowing these pH numbers helps us identify where the H plus concentration is by using these visual indicators. Let's take a look at how our pH meter works. So a pH meter, instead of using a color indicator, is actually going to run a voltage through your solution. So this is an example of a meter that you will be using in the lab. And what it does is it runs a current through the solution. So it runs a current through the liquid, and it uses that voltage difference between the solution and a reference solution that it has in order to determine the pH. This is going to be a much more accurate reading of pH of your solution. The way it works is it's got like a glass bulb here, and it has a permeable glass membrane that allows the H plus ions to be detected and essentially runs, again, an electrical current through the solution. And it compares it to a reference solution that's also in there. And so the difference in these voltages is what allows it to calculate pH. So it can see what what the reference is versus what your solution is, and it allows it to come up with that value. So for this lab, you're going to be needing to calculate pH. You're also going to need to be able to calculate pOH and go between the two. What you need to know about POHs is that it is related to pH in this fashion. So I always think about it like this. We had our scale of 0 to 14, and say our pH is 5. So that would be our pH. Our POH is the other part of it. Our POH would be 11, because it's the remaining of what's left of the 14. So that gives us this equation. Our pH plus our POH is equal to 14, because those are the different ranges that we have for those values. Let's look at how to calculate POH now, since we know how to calculate our H plus concentration from pH. So let's do the same thing here. So see if you can calculate the POH of a 0.01 molar NaOH solution. So you will need this equation here to do that. So make sure you have that equation written down before the question pops up. So in this scenario, remember that our NaOH, it splits into Na plus and OH minus, and all of those molecules split up into those ions. So that means we have 0.01 molar of OH. So in this case, our POH is equal to minus log of 0.01, which is the same as the last time that we calculated. So that gives us a POH of 2. Right. So if our POH is 2, then what should our pH be based on this equation here? So because our POH is 2, what's left over of that to get us to 14 is 12. So that's our pH there, which means it's a very alkaline solution. 12 is pretty high on that 14 scale, which makes sense because NaOH is a very strong base. So we have a very basic solution based on our pH. Now another thing that you might see in these problems is now that you have the pH, it might ask you, well, what is the H plus concentration? Now that you have the OH minus concentration, you have the POH, you have the pH, what's the H plus concentration? So let's take a look at that. So if we have a pH of 12, so if we use this equation, pH equals minus log of H plus, we know the pH is 12, it means we have 12 equals minus log of our H plus concentration. In order to solve this problem, you have to know how to undo logs, because we need to get the H plus value by itself, and so we have to undo it. So remember that in order to undo logs, we have an inverse operation. For log base 10, we undo that with 10 to the x. These are inverse operations, just like multiplication and division. Multiplication undoes division. The same way log base 10 undoes 10 to the x, and 10 to the x undoes log base 10. So if you had a graph like this, and this function that's plotted here is 10 to the x, which means it's going up exponentially, and we're seeing it increase very steeply like this. If you take this 10 to the x function and you put it on a logarithmic scale, sorry, I can't speak, a log base 10 scale, so log base 10 scale, you're going to see that this 10 to the x function is now a straight line. It undoes the curving of it. We know that this is a log scale because our first value here, 1, is log of 0. Log of 0 equals 1. Log of 1 equals 10. Log of 2 equals 100. Log of 3 equals 1,000, and so on and so forth. This is log base 10, and you can see that it's going up by increments of 10 because it's log base 10. And so that's how we know they undo each other, is because graphically we see this change. So let me show you how to apply this function now to our equation. Okay. All right, so if we want to undo log to get H plus by itself, we're going to do what math we can to isolate it. So I'm going to go ahead and deal with this negative sign. So negative 12 is equal to log of H plus. Just go ahead and take it over to the other side so it's not there. And then we're going to apply our 10 to the x to both sides. So 10 raised to the minus 12 and 10 raised to the log of H plus. What this does is it cancels these functions. Remember that 10 to the x It's the inverse function of log base 10, so they cancel each other out. And that's why we need to do that. And so when we write out our equation, we see that 10 to the minus 12 is equal to our concentration of H+. And then we can just put that in our calculator and we're done. So what that means is that for our concentration of our H+ ions, we have 1 times 10 to the minus 12 moles per liter of H+ ions. That's pretty low. That's a pretty small number, which makes sense if it's a basic solution. We're going to have very little H+, a lot more OH-, so that's where that value comes from. All right, let's see if you can do some example problems. So you have a pH of a solution that is 5.1, and I'm going to ask you to find the H+ concentration. Make sure that you use the equations from last time. If you need them again, they're right here. You can go ahead and pause the video and write them down. Okay, so see if you can calculate the H+ concentration of this solution. So we're going to use the same method that we used last time. If we have our pH, we can plug it into this equation. So I'm going to bring the minus sign over to the other side. I'm just dividing by -1 or multiplying by -1 in order to get it to the other side. All right, and then you can raise both sides 10 by 10 like that, and then you end up with this canceling. And this is the value that you should get for the molarity of the H+ concentration. Okay. So now that you've done that, see if you can calculate the pOH. So what is the pOH of a solution with this pH? To do this one, we don't need our answer for A. We're just going to use our pH. Remember that pH and pOH are, they add up to 14. So you can just take 5.1 plus whatever goes to 14, take the difference. And that gives you 8.9 equals your pOH. Right. Okay, so the last one is seeing if you can find the OH- concentration. So use the equations that I gave you and see if you can calculate this. Okay, so there are several ways to solve this one. I'm going to show you how to use this pOH equals minus log of OH concentration. If you're familiar with pKW, you can do this another way, but for this lab, this should be enough. So this is our pOH value that we calculated in part B, the 8.9. And we can literally apply the same algebraic method to get to our answer. I'm not going to walk through the steps. It gives us 1.25 times 10 to the minus 9. Molar OH. Okay. So we've got our OH concentration, our H+ concentration, and our pOH. And our pH was originally given to us. So that should be all of the values that you're asked to calculate in this lab.